CNT composites have numerous potential applications, although they are rather limited on the electronic side of things. Now, CNTs are very strong nanomaterials, which can also impact the kind of conductive properties that they give to materials. And in our case, even by using just 1% CNT materials, we get really interesting electrical properties.
Cool. So one of the things that's a challenge in the field is, understanding the impact of the polymer structure on the material properties, especially in the context of these composites. So there's a lot of people doing research in CNT composites in material science, but that impact of the polymer structure has really been less of a focus for the field.
One significant challenge for our case is really obtaining effective reinforcement of carbon nanotubes to the polymer chain through covalent bonding of, nanomaterial to polymer matrix. Often this is obtained through harsh conditions such as high temperatures and strong acidic conditions. However, we try to obtain in this project the same systems using mild experimental conditions.
So specifically what we use Diels Alder chemistry to link the carbon nanotube surface to the polymer matrix. So it's the same Diels Alder chemistry as you see often in small molecule organic chemistry, but we're using it here in polymer materials. The other thing that we're really interested in this project is developing dynamic and responsive materials, because that allows the materials to have properties such as self-healing. So if they become scratched or damaged in some way, we can actually recover the material properties.
Another aspect to this work is the possibility of accessing high-performing materials with different properties. And hence, in this case, we're interested in showing the correlation between polymer structure and material performance.
Yeah, and so in general in the field, there's a lot of interest in combining synergistic dynamic chemistries and molecular architecture to make high-performing materials. In this case here, we're using precision polymerization methods. We can really control where the cross-linkers are along the polymer chain and what those cross-linker functional groups are. And we use those to actually make our polymer matrix. We typically use a combination of hydrogen bonded units and also dynamic covalent units like those Diels Alder units we were discussing before.
For understanding the material behaviors, we focused on two main areas, which were the mechanical properties and electrical properties. For mechanical, we found that the CNT reinforcement led to some substantial increase in material strength. And this was pronounced where we have equal amounts of hydrogen bonding and dynamic covalent linkages. And for electrical properties, we showed really new cool applications, which I'll touch on in a bit.
Yep. So in the context of mechanical properties, we saw that, the benefit of adding these CNTs was really most significant when the materials were highly strained, right? So close to their breaking point. In those cases there, we could substantially strengthen the material by adding those CNTs. Interestingly, also, if we chose polymers where all the cross-linkers were in their own sort of parts of the polymer chain, we actually got stronger structures. But because all of our cross-links were actually dynamic, so hydrogen bonding and Diels Alder units, we can actually got self-healing properties in both the pure polymer matrix, but also when we added the carbon nanotubes.
Right. For the electrical properties, here we basically had three main demonstrations, right, where we highlighted the potential of these materials. And first is the strain sensing application, right, which is rather really growing in the field of medical device development. And we found here that these materials could respond to mechanical deformation or strain. And we showed that these materials are useful for regulating the flow of current. And we denoted this how by denoting that we could regulate the amount of current that flows into an LED bulb and regulate the brightness of the light. And then we also showed that, customizable resistors are possible where traditionally these sort of systems are from rigid systems that are not flexible. And so in this case, we showed flexible electronic materials for resistor applications, which you can get on demand without synthesizing the material from the ground up.
Yeah. So overall, this was a really exciting project. We're very proud to be a part of it, where we've sort of, introduced composite materials with self-healing properties. We've demonstrated new electrical functions like those customizable resistors, and also shown their potential in strain sensing. We hope that due to the dynamic chemistry within the material, we're hoping the materials will be able to be used for a long time and able to maintain their properties sort of benefit from a sustainability point of view.